Hi everyone and welcome back to Power Electronics Lectures. Today I'm gonna talk about the rectifiers with line impedance. To analyze the effect of line impedance on the output voltage of the rectifier, let's consider a simple diode rectifier with pure inductive load and a freewheeling diode. The pure inductive load, which is in reality a highly inductive load, can be represented as a current source on the load side, as you can see here on the right side of this three-phase diode rectifier. Look at this diode rectifier, a single-phase half-wave rectifier with a freewheeling diode, and also here we have a highly inductive load on the output. Highly inductive load means, or pure inductive load means the load has like zero resistive load and high value of the inductor, like the induction machine, for example. And this induction machine or this highly inductive load can easily be replaced by a current source. Why current source? Because if you remember, we said that the inductor hold the current, makes delay for the current, and when the inductor makes delay for the current, this means what? If we have small value for the inductor, then the current can be delayed for a small period of time. But if we have a highly inductive load, then this inductor can hold the current forever. So we can expect that the output current will be continuous all the time. No up and down on this current. It will be always continuous with a constant value. That's why we can easily replace the highly inductive load with a current source on the output to make our analysis. So now let's consider the input voltage here, which is V input, and the output voltage in this case, it will be a half wave of this input voltage, only this portion, and the other portion, this will be, it will not be on the output. So this is the blue line, is the output voltage, V output. Now, since we have a highly inductive load, then the output current, it will be how much? It will be something constant current all the time. So the output current I out, it will be constant all the time. And I can say that this is I out capital. Since the output current is constant, then we can easily say that I out is equal to how much? To I input plus IF, which is the freewheeling diode current. So the current here at this point, Kirchhoff's current law, I out is equal to IN plus IF. Since I out is continuous and fixed all the time, so when I input is 0, so IF will be equal to I out. When IF is 0, then I input will be equal to I out. So here we can say that at this point here, diode is on. Diode 1 is on. The main diode is on. This diode will be on because the voltage applied on this is how much? Is positive. Okay, and then the diode is conducting and diode is on, and diode F is off. So it's open circuit. So I input is equal to how much? To I output. And the current on the freewheeling diode is equal to how much? Is 0. Okay. At this point, since the voltage hits the 0 line, so diode 1, which is the main diode, will be off, and diode, the freewheeling diode, will be on, will be conducting. So the current will be moving in this direction, and the output current will be how much? It will be the freewheeling diode current. So at this point, this freewheeling diode will jump directly to be how much? To be the output current value. If you sum this value, the input and the freewheeling diode current, you'll find that this is exactly how much? The output current. So again, over and over, when the voltage became positive, so here, so this current will be I output, and this current will be 0, and so on and so forth. It's the same portion here. Okay, and here for all cases, this will be I out, the maximum here is out, and this is 0 ampere. This is I out, and this is 0 ampere. Now this is the behavior in a rectifier with a freewheeling diode and a highly inductive load. But actually this behavior is not always true, or it's not true at all, because practically this input here is not a pure wire. We have the line impedance, the cable that's connecting between the source and the rectifier. It has some impedance. Okay, so here we can add inductance here. And this line impedance also makes delay for the current. So at zero crossing here, when we have commutating between the input current and the freewheeling diode current, we agreed that the output current is always fixed and constant because the load is inductive load, a highly inductive load. So at zero crossing here, in a very short time, the input current is dropped to 0, and the freewheeling diode current rises to the value of the load current. As a result, so here if we said that this is the input current goes to 0, and the freewheeling diode current jump to the I output current. Okay, and this is I out. One of them comes to 0, and the other one jumps to the maximum load current. Now, theoretically, we said this time is 0, but practically there is time because we have line impedance. As a result, the di by dt, the rate of change of the current, is significantly large at this moment. So here, because this slope is dropping fast, so the rate of change of the current with respect to time is very large. So this will be very large value. Let's consider the line impedance effect on the input and the output voltage of this rectifier. At zero crossing, the input current is slowly dropped to 0 due to the input impedance effect, and the freewheeling diode current rises slowly to load current. Because the input current is constant, the output current should be equal to I input plus the freewheeling diode current. As a result, the di by dt value is affected by line impedance, and the rectified voltage and the input voltage are also affected because we have a short circuit in the transition period. So in the previously we thought that without line impedance, the behavior of the main diode and the freewheeling diode, it's something like this. The switch from this state, from this circuit state to this state directly, from mode 1 to mode 2. But if we have line impedance, as we said, the impedance or the inductor hold the current, so it takes time for the current to move from the conduction mode here, from the I output value to zero value. So it takes time to reach to the zero value. And also for this current here, it takes time to move from 0 to I output value, to the load current value. So this transition period, here and here, you'll find that this diode is conducting and also this diode is conducting. So when we have line impedance, things is not jumping from this state to this state. No, the behavior will be like this. We have mode number 1, we have mode 2, and I will say that we have mode Z. So from mode 1 to mode Z, then from mode Z to mode 2. So this here, the time that the rectifier spent in this mode is a very short time, but at the same time we have short circuit at the input of the rectifier. So the voltage from here to here is 0 at this very short time. Let's draw the waveforms again for the input voltage, output voltage, and the output current, and the current in each diode. And as we said in power electronics, the driving force here is what? Is the load. As you can see here, we have inductive load. So I'll draw the current first for the inductive load. It's a constant value, I out. Okay, so I out here has a constant value, I out capital, the load current. Then we'll draw the currents for the main diode and for the input current, which is the current through the main diode, and the freewheeling diode current. So here we have the input current, I input, and here we have the freewheeling diode, IF. I will consider that the current, and this for this half wave, we have D1 is on and the freewheeling diode is off. Okay, and at this point the main diode is off and the freewheeling diode is on. So when the main diode is on, this means what? This means the input current is equal to the output current. Now, at this point, we have transition. The current became, the voltage across diode 1 became 0, so the diode 1 must be how much? Must be off. But because we have current here inside the line impedance, inside this inductor, so the current will take time to move from I out to the 0 value. So this would spend some time to reach to 0 value. Same thing will happen here in the freewheeling diode current. So here we have 0 current, 0 ampere, and this will take time to reach to the maximum value, which is the load current. And this one, same thing here will happen. And for the input current, also same thing. Now we understand that there is delay for the current transition from 0 to load current and from the load current to 0, and the load current is always constant, no problem. But let's see how the output voltage the load voltage looks like, and how the input voltage from here to here looks like. So the load or the input voltage and the output voltage. If you look at the output voltage, for example, here, we understand that at this point from here to here, let's look at this cycle, for example. When diode 1 is on and the freewheeling diode is off, so this means the output voltage must be equal to the input voltage, right? So you can say that from this point to this point, from here to here, the output voltage will be equal to the input voltage. And the same thing for this period. From here to here, so let's say that this is T over 2, and this point here is T. So the voltage here, it will be equal to the input voltage. And here is the same thing. It's just the positive side of the sine wave. Now, from here to here, at this time, at the transition time, diode 1 and the freewheeling diode are on. So this means the input voltage is 0 and the output voltage is also 0. Because this diode, the freewheeling diode, will be short circuit, so the output will be how much? It will be also 0, right? So the voltage from here to here is how much? Is 0. So as if we have a small portion here is eaten or taken from this output voltage. So it will be something like this. So this will be 0 volt. And the rest will be the input voltage waveform. How the output voltage will look like? So this V out in the blue line, and let's draw the input voltage using the yellow color. So the input voltage is like this, and from here to here, the negative side, the negative half cycle, it will be like this as well. Why? Because also here at this point, the negative half cycle, diode 1 and freewheeling diode is conducting, so the input is 0, but the output will be 0 as well because it's rectified. There is no voltage in the output. So here we have the same thing. So this is the input voltage, the yellow color, V input, and the blue color is the output voltage. How to calculate the average voltage for this rectified output? You need to find the commutating time. So we need to find when this voltage hits this value, or when this voltage, the freewheeling diode and the main diode, will be released from being both at the conduction mode. To calculate the commutation time for this portion from here to here, we can just say that at this moment, okay, at this moment, when the input voltage is 0, so here we have the input voltage, and here we have the line impedance, the inductor, and everything here is 0, right? So we can say that this voltage from here to here is equal to the voltage across the inductor, which is LDI by dt. So we can say LDI by dt is equal to the voltage, the input voltage, which is V maximum sine 2 pi t over t. We can use this equation to find the period from here to here, and then once we find this value, we can easily find the value of this voltage we deduct the value of this voltage from the whole sine wave, then we can find what the average rectified voltage of this kind of rectifiers with line impedance.